the Shell presentation, challenges and opportunities in lubricating integrated systems. So what does that mean? What's the premise? So when we were speaking to John here about the presence of doing a technical lecture, he talked about, you know, what's going on in hydraulics, what's going on here, and what are some of the changes that he's seen in the industry. And a lot of those changes are coming from the, you know, the integration of the systems. We've all heard the buzzword, you know, Industry 4.0, Internet of Things, you know, the connectivity of the machines. So that was really the premise of the short lecture today. But also, how does that affect what we do on a day-to-day basis, A, in fluid power, and B, specifically through lubricants. So how do those challenges affect how the product works in operation, but how lubricants are designed, and what are the important factors? So that's really the premise of the presentation today and how we're going to do it. So by way of introduction, my name is Andrew Gibson. I'm the marketing manager for Shell here in the UK for the lubricants business. And my colleague Peter Murray is our product application specialist on the lubricants side. So, and Peter will introduce himself as the presentation starts. So, just coming back to the kind of context and premise, you know, we talk about not to have lots of different buzzwords, but you know, what's going on, the application evolution, the constant change. So, you know, some things change at a fast rate, some things change at a slower rate. How is the industry dealing with that, and how does that kind of evolution manifest itself on a day-to-day basis through our eyes as a lubricant provider? So, but if you look at it, you know, we talked about advancing technology. We talked about here in the UK and globally, you know, new assets, you know, the advent of not so much the pump or the gearbox changing, but the controllers changing, the sensors are changing. You know, how does that affect things on a day-to-day basis? And then we all live in a modern world. You know, post-recession, there's less and less people. You know, we're all in the industry where we've all been in situations where perhaps there was 20 people doing a job, there's less and less people doing the same job in our industry. Secondly, you know, we're talking about a skills shortage. People on the ground, because they are busier and busier, they have less time to go into the detail. So does that necessary skills in the areas where we need to have those skills, does that necessarily exist? So that's really the kind of context. And again, I've just put some words up because our language is changing. You know, people in commercial jobs, who sells products anymore? Now, everybody sells solutions, you know, but those manifest itself in the product and the product technology that we bring there. You know, we talk about outputs, you know, or is it outcomes now? It's the subtlety of the changing of the words. So are those words any different? You know, people say, you know, if you buy a car, you don't want an engine to go around. Now you want a car to get to so much in so many miles per gallon, or you want a factory to produce so many units whilst being, you know, particularly efficient. So what we're going to do today is just to look at the next level down, as I said. What are some of the changes, and how do we view that as a lubricant provider, you know, within the fluid power industry? So, on that note, I'll pass over to Pete, and we'll go to you.
Thanks, Andrew. Andrew gave me an introduction there. I'll just repeat it. My name's Peter Murray from Shell Global Solutions. Pete, if you want to speak to me, that's how I prefer it. I've been in lubricants for some time now, and also spent a lot of time in industry myself, so it gives me a good foundation for this little seminar today. What I've just put up on this slide here, in the context of increased automation, integration, that's one of the things that's changing. On the left, I've got this power ability variable load. You know, there's a lot of variable speed drives coming in, and I'll position this as well just before I go any deeper. I'm not just talking about hydraulic systems here today. So hydraulics, gears, turbines, greases. and a few other things if the conversation takes us there. But so not just focusing on the hydraulics, although it will be a good chunk of the presentation. In many of the machines that I go along to see, the half the size that I saw 15 years ago, doing the same work, so their footprint has reduced significantly in that factory floor, workshop or whatever, but the power that's going through them has actually increased, so a massive increase in the power density of the machines. Sump designs, residence times on some of our hydraulic systems today, well, they haven't got one. You know, the oil goes round from the pump, does its work, and it's straight back up the same pump and goes off to do it again. There's no time for it to catch its breath in many systems, particularly in the mobile arena. Some tolerance on the static one, but even then, residence times and sumps are reducing. Oil change frequency. Extension of oil life is what that refers to. People wouldn't really want to drop the frequency of the change in the oil, for obvious reasons. So the strive for a longer life is forever there. And efficiency requirements. And when I'm talking about efficiency requirements, I'm talking from an end-to-end process, so factory in, factory out. The ability to operate efficiently within the realities of life. So if your supply chain dries up, you might say, well, today would be a good day to slow that process down a bit because electrically it's more efficient doing it. And it's going to reduce my oil temperatures, that's going to extend the life of my oil. You know, this sort of agility in a machine, a factory is quite common. Which actually leads us to, the primary subject today, this dependence on feedback systems. So it's not just talking about flows, temperatures, pressures, but also position. Many other myriad of local inputs, but also production line information. The ability, I need more further down the line, I need it quicker, so you're going to speed up this process. Or I need less, or there's a supply chain constraint that says, right, well, let's just slow the whole process down. All of this is what we do for a living, isn't it? Living under these realities. Many of it's done in our head. But quite a complicated slide there, if I was just to emphasise this bold statement. I mean, the number of sensors we see today that are influencing a machine's operation has just increased incredibly. As I said, it's not just the local environment, the machine itself, it's feedback from all sorts of other sensors that are influencing the operation. How does this demand influence the performance of a lubricant selection? I mean, that's where I'm coming from today. It does make a difference. In that complicated, integrated world, we're looking for a lubricant that it's got this enduring, predictable, optimal performance a long time. People want to run for a long time, so minimal maintenance. They want the machine to operate the same way every time. And they also want it to deliver under constantly changing loads. So the variable speed, if I take an air compressor for instance, variable speed drive, very common today in the air compressor world. So you have two machines doing the primary load and then another one that's just going to ramp up and ramp down as the air demand in your factory changes. The temperature of that lubricant is going to respond accordingly. That, in a small way, it's a feedback system, but it does influence the selection of the lubricant you might want to use in those compressors. The ability to operate effectively over a wide temperature range. There's a series of slides just going to come on here, and I'll start it with thermal stability, oxidation resistance. These are kind of the two of the key things when we talk about lubricants, as in longevity, how long they might last. Thermal stability, well, let's get back to that. It's an easy one there. Resistance to heat, how quickly or how much will it degrade when it's subjected to a lot of heat. You can do a lot with lubricant selection to combat heat, with heat resistance. Oxidation resistance, I mean, this is just about getting old. Sadly, it happens to us all, doesn't it? You can retard the effects of oxidation very effectively with base oil selection in the first place, and a suitable additive pack to go into. Lacquers and sludges, and we spoke to a friend here earlier on, lacquers and sludges. If you're in control systems, will it be hydronic, as in this sort of hydraulics we see here today, or turbine control system, this is a nightmare for you. It's really going to mean, if you get sludge and varnish formation in a control valve, move valve, something like that, and you're anticipating the machine when you tell it to slow down, move up, or move, and it doesn't, then you've got a serious problem. Particularly if it's an emergency shutdown situation, something like that. We don't want to do emergency shutdowns on turbines ever. It does have to happen, sadly. Working on or developing products that can resist the formation of sludges and varnishes in the first place is the approach we take. Acid formation, well, sadly that's a part of the ageing process, but you can resist it. Air release, now it's kind of key in the hydraulic world, but also in the turbine world. And this is, if air does get entrained into the system, how quickly it will release out of that fluid. Do a lot with that. Water separation, self-explanatory. Corrosion protection. Now we do a lot of things with corrosion protection. We do our very best to keep water out in the first place. We fit desiccant filters and marvellous, but this stuff still manages to find a way in and can be a catalyst for corrosion. So once it's in, we can do something from a lubricant side to help with that. In the variable speed or feedback systems, where sometimes you'll have machines lying sitting there doing nothing at low speed, and then they go up to high speed, you can get corrosion issues if there's any moisture coming, a duplicate change, things like this. So it's a key one for feedback system. Low foam forming tendency. I think everybody's seen some oil foaming in their machines. Basically, it's, a lot of it's air entrainment. You want to minimise the effects of that. Next, I move on to another column actually here. Integrated machines, by their nature, are part of something bigger. And quite often I come across, I'll have a hydraulic system, but it's also actually asked, the very same lubricant is asked to look after a set of gears and bearings as well, and some associated component on the machine. So in the specifications for the hydraulic system, I'll start to see a lot of gear oil and bearing specifications or requirements because of this demand for an integrated fluid. This is one, very easy to think, seals. It's a real challenge in today's world, making products that are compatible with the seals of choice of the OEMs. They do a lot of work in the OEMs themselves, in selecting the right seals, internal paints. We actually have to test our products on external paints as well now to get approval through OEM. So if it's spilt on the machine, you've got to make sure that our product isn't going to take the paint covering off the outside of the gearbox or pump housing. Ability to perform with water. Stick slip performance, I think yourself, you've talked about your actuators. I think you were, just before the seminar started, you were involved with actuators, hydraulic ones. Stick slip performance is key on those. In our hydraulic world, we want that hydraulic actuator to move at the rate we want it to move at and not be a series of judders. We want it to get there at the right. That is an attribute that can be affected by the lubricant selection, and a lot of the OEMs will ask to see that. I mentioned before the anti-wear. You also see this extreme pressure performance, EP. I think everybody's met it in the engineering world. This acronym EP for extreme pressure. It's really a gear tooth protection number, qualification number. You see that on integrated machines. These are machines that are doing many more things than just the basic hydraulics. They're doing some gears and bearings as well. So that is, it's an ever-changing thing, and the requirements are going up and up and up. Viscosity index, its index and the stability. For this one, choosing the right viscosity is key to operation. Viscosity index is a measure of how much that viscosity is going to change with temperature. We will engineer our fluids, selection of base oils, maybe not an additive to support the index, but the stability is the key word when we design it and produce it. We want it to stay as stable for as long as possible. So this is the predictable part of lubricant performance. On a Monday we start with this index, Friday, the month later, the year later, the 2 year later. We want to see the flattest line in that index. Cleanliness. See by some of the badges here, obviously there's people from the filter world. Crucial in the hydraulics, absolutely crucial. More and more and more I see the demand for cleanliness in turbines and gears as well, even on some of the more viscous products. They're really asking for cleanliness. I spend a lot of time in the wind turbine area. The levels I'm seeing there are not as, they're approaching the hydraulic requirements for cleanliness. And that's for a 320 centistone product, not a 32 or 46, 60. Filterability ties in cleanliness, but this is really the ability of the finished fluid formulation to stay intact when subjected to fine filtration. There's a few different options on that, but importantly, compatibility with other products. The evolution, we see, I go into a factory or whatever, and I will see a combination of a well-established asset in that factory, and then a new one as well, and then perhaps an older one. And we've got to make sure that the products will suit all of these machines as well. So there's an element of backward compatibility. It is important, because the same fluid is probably going to service the older and the newer. HS&E compliance, it's a given for all of us today. Yeah? And sometimes you'll find all the peculiar OEM requirements. If I was to pick a few things out, I'll tell you what, let's go back on slide. Before I go on to my next slide, is there anything on that that you'd like expansion on, or perhaps raised thoughts or questions in your mind? I would welcome any. Okay, I shall move on, but if something does, please do just stick your hand up, shout, Pete, and I'll do my very best. If I was to pick from that previous list, say the top 6, this is what I would pick as the top 6 that are key for the integrated machine, as we've discussed it today. Discussed the index, I mentioned that. This is the we discussed the I've discussed the index. If we're talking about machines that are operating in extremes of temperature, so as I mentioned, I do wind turbines. I've got one in China, C minus 40 in their winter, and then up to plus 40. This is ambient temperatures in their soil. I've got to put a product in there that can operate in their different operating regimes, and they do have different ones for different climatic situations, but it's got the same product in there. It's an agile product that can take in, responds with all these other inputs, and provides the level of protection for the different operating modes. And this is because, in that example, high viscosity index, I've got a product with a very high viscosity index. It changes far less than traditional mineral oils, for instance, and can provide working protection, say from, in this case, minus 40. Then the final operating temperature is plus 60, and that's what they control with it. And to do that, you need a high viscosity index. It actually wants to last a long time in shear stability, because some of these products, not in that example, but all more viscous products might have to be thickened with a polymer. We don't want that polymer to be ripped apart. So the selection of the right polymer for these high viscosity products is crucial if we want them to hit the long life. So there's a lot of things balancing up. Temperature, low temperature fluids to use in my wind turbine example. The advantages are written there. I can get more power out of this asset with this product than I can with others. Better news can you tell your boss? You're producing more power with this one than you previously experienced, or what you actually change is the resistance to oxidation, better lubricity, and lower volatility. These are the final things. There's the final 3 out of that previous list that I'll be looking for. Has that prompted any questions or thoughts in your own particular applications?
I'll give you a question.
Please. Please, I can do with it.
I work in the mobile plant forestry industry.
Okay.
We use a lot of 32 hydraulic oil. Big difference on the different suppliers on its ability to take the top end temperature.
Top end.
Because particularly within forestry, temperature is an issue. Quite often we're hitting 72 degrees centigrade during the summer when hydraulic systems, although they're all supposed to be working at 60. Okay. And like the GCB oils, they sort of advertise the fact that they are able to work at a slightly higher temperature or survive better at a slightly higher temperature. We haven't experienced that, but basically finished manufacturers specify 32, but they don't say who's 32. and we have seen a significant difference between different manufacturers of oil.
And when you see a difference, how does that? What's the difference manifest itself as?
Usually, the most obvious one is discoloration. Obviously, it's oxidation is what you visually see. What you experience is more seizure of valves when it hits the higher temperatures. Manufacturers reckon we've no problem with cooling, but this has been going on for 20 years with 4 different major manufacturers. But it seems to be a British problem.
I mean, it's they're not all the same. 32 centistoke indicates the viscosity at 40 degrees centigrade. The viscosity at your operating temperature, so if you're at 75, it's going to be a lot less. You know, so I can't imagine it's probably 4 or 5 or 6 centistokes. I mean, as a fix, the first thing I would do is move up, possibly to a 46 centistoke. Yeah, it's an easy step to do, and probably would be very well accepted by the OEM as well. I would imagine. As regards the effects, how does it manifest itself? You know, if it's causing if the temperature causing premature oxidation, then move up in the quality of the lubricant. The things to look for are its resistance to oxidation and thermal stress. Those are thermal stress is the key one here. Oxidation actually goes hand in hand. And you would find from most of the higher end lubricant manufacturers, I include ourselves there, but I'm not trying to be sell Shell. Look for the resistance to oxidation, and you'll see these numbers tossed, blah blah blah. Sludge formation in different tests, and you can actually do a little bit of benchmarking. You'll see a vivid difference between the high-end manufacturers and others. Now I'm selling Shell on the one that we're moving to this year, the Tellus S2. That's a change in base oil, which is particularly resisting aging and the effects of thermal degradation. So I can touch on that in a second, but thanks for that. I mean,
on that note, it is noticeable that the higher brands don't allow machines to heat as much. That's kind of customers' feedback.
They don't allow
the machines to overheat as much, so therefore we come in within sort of 65, 68 degrees. But if we use 46, if you get a morning sitting around about 5 degrees centigrade, proportional valves take at least another half hour to warm the system to get them operating properly. And customers being customers don't accept.
Yeah, I mean, if you talk about system warm up, so operation from cold, then go for a product with a higher viscosity index. So you'll find hydraulic fluids designed for use within a factory, and they will have a viscosity index of, at the low end 96, just a number, this index, at the high end probably 104, something like that. When you move to forestry, classically you would use a product that is designed for a broader temperature range, where you have a viscosity index somewhere 140. I can give you some help on this one if you want of how to actually pick them on what these numbers mean.
Our problem is educating the customer.
Yeah.
That is, if it was left to ourselves, there's not a problem. It's educating the customer to know this.
You mentioned engine oils. I can understand, really can understand why it's so tempting. There's a couple of challenges with using engine oils in hydraulics. One, it's a detergent oil, so any water that will get in there will always form emulsion, it will never separate. Now, for some operations that's actually fine, for others it is not. The one that challenges myself, and just from more experience, is the anti-wear package that's in there is not designed for a hydraulic pump. It's designed for a piston ring, cylinder liner type mechanism. So it could well not, might not be the optimum anti-wear one for the service. But I understand the attraction of using an engine because we've got them there. Yeah.
Well, a lot of JCBs now are not engine oil.
Yeah.
Because it's got a bit of viscosity. It lasts long.
I would think it lasts longer in some measures. You know, one of the other challenges I see with engine oils is the sheer stability. This is, if it's an engine oil, it is a viscosity modified product. Like a dual viscosity SAE rating, so 530, 1040, 15, something like that. If it's got those, then it has got a polymer element in it. And the polymer selection has been made to suit that engine oil service, as opposed to the hydraulic pump service. And if we think about the machine internals, they are quite actually different mechanisms.
Yeah.
And that's where I'm slightly uncomfortable. I mean, I know some good friends at JCB. It was a neighbour actually. It's quite scary. But their advice is coming from you know, an end-to-end perspective. It works for their customers. They've got the product. You can see why they go in there.
Because if you have a pump reservice from them, they said to you, if you don't put engine oil, then you're not warranting it.
Okay.
So
Well, there's a good incentive,
It's
isn't
just to do what you tell me, really, isn't it?
Yeah, yeah.
Are they using that for hydrostatic systems as well, or just
Yeah.
pure hydraulic?
Hydrostatic.
Because we saw failures with hydrostatic systems using engine oil. Also using bio oil. Cold temperatures, you get separation within the pump casing, bearing failures.
Yeah. I mean, there's a whole host of opinions.
No, it's interesting to see,
Yeah.
because things step on, things move on. So.
The different grades of engine oil now are a lot better than before.
Yeah. Without a doubt, they are.
So
Yes.
it's not like you're chucking something that you're chucking an old Cavalier, is it? It's
No,
you're
yeah.
putting out something a lot more better.
It's a good point. The sheer stability that you have today on an engine oil is far better than when we were using 2050s.
Less sulphur. Less sulphur,
Yeah,
which
it
is
was all
really
that.
cool.
Yeah. Big benefit of the group 2 that we're moving to. How are we doing for time? Mike? 10 minutes. Okay. The last slide. Got two. Got any questions? Please bring them in. I've just put up on here 4 examples of what we're doing to make these more agile products for the integrated systems, and we've touched actually on the top one there, lower sulphur tight tolerance group 2 base oils. What does lower sulphur mean? We're all used to looking at yellow, amber coloured fluids for our you know. Well, the colour comes from the sulphur content. That's what colours the oil. If you take it out, it goes almost to a water white. Which you'll see in a lot of synthetic products, Alta-2 anodes, all water white. Sulphur is a good thing to a certain extent. It's a double-edged sword, to be honest. It can provide wear protection, but it can also be a catalyst for acid attack, sulfuric acid. So we've made a decision we're going to go from group 1 of those more traditional types to group 2, so it's a lower sulphur concentration. The production process is a lot tighter. So when we go into our production process, so production process of the base oil is a lot tighter. When we then go into the bulk blending of these, this is a great advantage. We know how strong that chili is. You know, we've got a recipe here. We know exactly far tighter tolerance. It means we can produce tighter tolerance products at the end with predictable performances. We haven't got to cater for everything. All group 1 products you might find on the world. Second big advantage, it's oxidation resistance. Group 2 products respond extremely well to antioxidants, to prevent aging, really. Extremely well, far better than the Group 1s. So, along the line, for resistance to oxidation and thermal degradation. Gear oils. The synthetic polyalpha olefins have been with us some time, but they, like everything else, are changing. The catalysts used to produce them are also evolving. So we're moving to some of the most advanced ones you can get. And for my worlds of gears, it actually gives me fantastic low temperature fluidity. Big advantage. Turbine oils. There's a term up there, we've been using Group 2 base oils, really good base oils, but now we've decided to go to Group 3, or this, in our Shell word, gas to liquids. Is this a term people have heard of? Okay. Gas to liquids. Shell has got the biggest investment for 10, 15 years in Qatar, where they convert gas to liquids. The primary target is fuel. This process can also used and is used to make base oils. The beauty about this is the characteristics of this Group 3 gas liquid product is that incredibly tight tolerance, low sulfur. We use it in our turbine oils. We use it in our transformer insulating oils. We use it in some passenger car oils as well now. But it's one of the key things that it does is this low varnish forming. So control valves in turbines. It's a real star in this performance.
Can I ask a question on that, please?
Please, yeah.
How does the conductivity of this gas to liquid compare with the Group 2 base oils? Conductivity. Because that's been an issue with turbine oils in the creation of varnish and sparking.
Conductivity is always going to be an issue because turbine oils typically will have no metallic adivation in them and no metallic components. It's all organic chemistry. Okay, so this is like a fundamental. Why does it happen in turbine oils? And because it's organic rather than metallic chemistry, it doesn't want to conduct. It's actually an insulating oil as well. So when you get to the conductivity issue, which is really, I think you going towards sparking on filter elements and the difference between the Group 2 and that I cannot answer. And I'm not going to guess. I can find the answer for you if you'd like to leave me your contact number, but it's micro Siemens per metre, I think you measure it in, don't you? Conductivity. But what is the difference advantage? I can certainly find out for you there. But fundamentally, that's the issue with turbine oils, is because they're using organic chemistry, not in their additive pack, not a metallic chemistry. They're insulating oils. But please leave me details and I'll try it down.
Thank you.
And grease is at the bottom. How are we doing? That's right. It shouldn't be at the bottom. We ignore greases. The advancement in greases has been subject to the same things we see in fluid lubricants. A grease is made out of three things: a base oil, a thickener, and an additive pack. So the advantages we see in the base oils, for instance, in the top ones, the hydraulic gears turbine, are applied in the grease. So high viscosity synthetic base oils in greases. And it gives the same advantages. And if you've got machinery that gives variable speed, I mean, many of us have seen we've all got variable frequency drives now. So you've got the electric motors that are running on 12 hertz up to 72 hertz, and rotational speed changes. Well, when you change the rotational speed, the viscosity requirement changes as well. How can you cope with that? The agility is, you can use a high viscosity index base oil within that grease, and it will cope with that rev range far better than a standard viscosity index. Mechanically stable thickeners. What does mechanically stable? It means mechanically stable is if you started off with a grease and you basically measure the consistency by dropping some cone in it and see how far it dips in. It's a really rough measurement, but if you work that grease and work that grease 20,000 times, when you then do the same measurement for the mechanically advanced one, it will be far closer to its original measurement. For our older greases, standard lithium greases for instance, mechanical stability is not the best at all. So now we use lithium complex greases. And I've given the example there, the low maintenance electric motors as well, that's variable speed and the desire for, not to be greasing the motors, not sending the electrician or the fitter out to do this. On one of ours, I think ABB motors, we've got a double, half the frequency or extended the regreasing interval out by 100%. These are the things that we have to do. Any other questions? Well, thanks for your time, your attention, and the questions. I hope it has been some benefit to you. And please, if you can leave your details on, because I've seen that question asked, and I know the man to ask. I'll send this one to him. I'll find that. Okay. Thanks very much.